My name is Sean Barr. I'm Vice President with the Austin Company. We're based in Cleveland and have offices around the country, Europe, and Mexico. My background, I'm an industrial engineer by training. I worked in manufacturing, food manufacturing for about 20 years, got a master's in project management along the way. And during that time, as I was an industrial engineer and working on commercialization, for food products, for co-packers and things of that nature, come to find out that we needed to have a really good methodology for determining capacity for production lines. So kind of went through that and came up with this approach through a theory of constraints. So that's a little background I'm going to just kind of present. Okay. Theory of constraints for the food manufacturing. What is the theory of constraints? So basically, the theory of constraints is a methodology to identify the most important limiting factor, the constraint that stands in the way of achieving the goal. Then systematically improving that constraint until it's no longer a limiting factor. In manufacturing, the constraint is often referred to as a bottleneck. So we've got a nice little graphic here that kind of goes through this. So our approach is to, when we go into food manufacturing, there's lots of different types of production methodologies, equipment. What we want to do is look at the production line. We look at every piece of equipment in the production line individually to determine its own capacity. So we evaluate each piece of equipment we look at, and there's lots of different ways to go about this depending on the type of equipment that we're looking at. It could be a batch operation, it could be continuous operation, and packaging. All of them have specific approaches to consider when identifying their individual capacities. We want to, through that, we will identify the capacity restraint or bottleneck for the production line and try to understand why is it a constraint? Is there a reason? Is there something we can do to increase this production capacity so it's not the constraint? If it is the constraint and it is going to be in place in the future, we want to make sure that there's plenty of capacity before and after that, so that bottleneck or that constraint is always utilized as much as possible. So once we identify that, we adjust as we can to accommodate the target volume. And then we identify the raw material, work in process, and finished goods storage requirements all around the production process and the constraint. So our objective is in this, we have a case study that we did a few years ago. This company, we went in and worked with them. Their goal was to increase their production capacity from 12 million pounds a year to 45 million pounds a year. I'm just going to kind of walk you through a high level analysis. So when we get into this analysis, we have to identify what are the parameters for the operation. So we want to understand any of the yield implications. We want to understand how many weeks per year we're working, how many days per week and hours per day, and the annual volume and the target volume. So then we can take all of that. That's a basis for how we want to improve the operation. Now, there are some improvements that we can make right here. I mean, instead of 9 hours a day, maybe we go to 2 shifts, things of that nature. But this is the basis for the evaluation. Then we want to start looking at the process. So most processes, we start with receiving and going to a raw cooler storage. We need to see, based on the weight per pallet or combo and a utilization factor, how many storage spaces do we need to make sure that we're not going to create a constraint with storage. So we go through and look at the combos required, the utilization. We don't want 100% utilization of the cooler. That would mean every space is filled, and we got to have room to operate. So anywhere from 70 to 90, depending on how it is managed, is typical. Then we determine the pallet spaces required, and then the square feet. And then we'll look at the layout, aisles, spaces, and things of that nature. Then we go into the process. Now, this is one process. There are many different processes out there, but this is just an example. On this process, we started with injection. We take the meat in the raw combos, we dump it onto a line, we run it through an injector, we look at the percent injection, by product. When we start looking at the process, there's lots of different processes out there. But this is a particular one I chose just as an example. This one starts out when you're feeding the raw combos into the injection line. So we look at the injection percentages, the total volume of injection over an annualized basis. Then we run through a finished yield percentage. We incorporate efficiencies to determine what the capacity is for that particular piece of equipment. And then we look at, do we need multiple of those, or is that one okay to hit our ultimate goal? And as we move along, this particular process went from injection into tumbling. Similarly, we're looking at the pounds per tumbler. How many minutes does it take to load and unload? What's the cycle time? So we want the overall cycle time. We apply an efficiency. Typically, we'll start out with an 85% efficiency, and we'll work with clients to determine what that target should be. But 85% is world class, so that's a good starting place. This particular one, we used 80%. Then we look at the pounds per tumbler, number of tumblers, and extrapolate that through the previous established parameters to determine the annual capacity. Then we can look at multiples or larger pieces of equipment to ultimately reach our overall throughput requirement. This particular product came out of the tumbler, and it goes into a horizontal roll stock packaging machine for cook in a bag application. So this particular one was a multi-vac. We're going to look at the cycles per minute, the pieces per cycle, and then apply an efficiency factor, as we previously mentioned, extrapolating that over the hours annually worked to see what the capacity for that piece of equipment is. Similar to the tumblers, we're looking at the future requirements. We've got existing, we got new, and then we look at different alternatives to make sure that that can meet the ultimate goal of our annual target. This particular process, after the cook and bag, went on to product, it went on to racks, and then it went into smokehouses. So from this application, we're looking at how many houses do we have, how many pieces of product go on to a rack that gets rolled into the smokehouse. Then we look at the racks per house. We look at the cycle time. How long does it take to load the house? How long does it take to unload the house? What's the cycle time? So we're looking for the full cycle time. We apply that over an hours available per day. Typically on smokehouses, we're going to operate a longer period of time than you would production because it's a longer cycle time. And with a little bit of time in the 24 hours to clean and prep it for the next day. So we take that. Similarly, we look at the number of ovens, apply any future applications, additionals, look at the efficiency factor, and then extrapolate that over the annual to see what we know, if it meets our objective or not. Now this one, this particular process, the cook in the bag product, some of it went straight into packaging. Some of it gets finished. So what we did was take the packaging off the cooked product, and then we put it on a belt for an impingement oven for finishing, different types of finishes, oven baked, and any flavorings and additives you might put on the surface for treatment. And then it goes to repackaging. So this one, since we're looking at a linear oven, we looked at the length of the belt. That's the effective length of the belt that's in the heating areas, the width of the belt, then the product size. And then by looking at the product size and the belt loading, we can determine the per square foot, how many pounds are we going to be able to load on that belt. We look at the dwell time in the oven, and then apply, of course, the efficiency and extrapolating over the hours run to see what that capacity is. Now, since it's only a portion of the overall volume, we don't have to worry about hitting our ultimate goal. We just have to worry about hitting the percentage of the total goal that's going to have this particular treatment. So in this application, we had a current oven. We proposed adding one so we could meet that requirement. Then we get into packaging. On this one, it was a rotary vacuum machine, 8600 cryovac. And we looked at the pounds per piece, the pieces per minute. Now, on the pieces per minute for all this equipment, we always go back to the original equipment manufacturer, the OEM, to see what the rated speed is. Some manufacturers run equipment a little bit faster than the OEM will state that is possible. Not that we've seen that happen out in industry, but I'm aware that it does happen. But when we're doing the calculations, I always go back to the OEM stated capacity because, or pieces per minute, because that's what they're going to guarantee. So I like to base an analysis on a guaranteed rate. We take that guaranteed rate based off the cavity size, the product, and then apply an efficiency. And there again, extrapolate over the hours per year to determine what that capacity needs to be. On this one, everything went through this packaging machine. So we're looking at our overall annual requirement. And we determined that we did need to add one machine. And a new machine could run faster than the old machine. And the old machine in this application, we were able to make some modifications to it, increase the vacuum pump size, so we could increase its pieces per minute as well. But it just wasn't enough, so we had to add a second. Now, since we've gone through this particular process, we've identified capacity for each one of the pieces of equipment in the process. Now we want to roll that up into a recap. So you can see here that we have the injection, tumble, horizontal roll stock, smokehouse, cyclone, and cryovac. Now, it's very simple in Excel. I go in and do an at-min statement, which makes it very easy to pull out what the capacity constraint is, your lowest number outside of the cyclone, because it was going to only be doing partial of the product. The smokehouse was our capacity constraint. So on current scenario, they have capacity to do around 20 million pounds. We wanted 40, so we extrapolated smokehouse to get it up to that amount. It's still a capacity restriction, but it does exceed our annual capacity requirement. So with this implementation, we not only meet our goal, but we have capacity to grow a little bit past that, which is never going to be a bad thing within reason. So this identifies our capacity constraint and verifies that annually, based on all the assumptions that we've agreed upon and discussed, we'll be able to increase that. And then we'll take that and come up with a plan on how we're going to implement this. We work on the layout to accommodate the new and replacement upgraded equipment. So on this particular one, we had additional space and equipment must be purchased and accommodated in the renovation expansion, including we needed 157 more raw pallet spaces. We needed to add an injector. We had to add 2 tumblers. We demoed some smokehouses and added new ones, so that increased the capacity there. It was still the constraint, but that was okay. It met our objective. We added the oven, and then we added a packaging machine to get to the ultimate requirement of what the client was looking for. So the benefits of this type of analysis. Now, this was one example. I mean, we all know that there's a myriad of applications out there, and every one of them is specific and unique to the products and the customers that are using them. So every one of them, it's hard to do a boilerplate on any of these. Every one of them have to be evaluated independently and specifically to understand what the requirements of the clients are and what they're trying to achieve. We have to consider the products, the product characteristics, and many things come into play. So the benefits, identifying the existing capacity constraint is a tool. It's a tool needed to ensure maximum volume. I've had situations where we've done these analysis, and without changing anything, the client was able to increase their production capacity. Now, my opinion is that they were able to do that because they were able to see what was achievable by identifying the bottleneck in the process and focusing on making sure that that particular bottleneck got the highest efficiency possible, that it never shut down, that was always fed and had somewhere to go with the product. They were able to increase their production capacity without spending a cent other than having the evaluation done. The number 2 here, production process is evaluated to analytically replace or add equipment, such as we went through an example. And the facility layout, as I mentioned, we take this as a basis for understanding what needs to be done to the process. And then we take that to the next step. We take the current layout. We start looking at how can we accommodate additional equipment. Sometimes we can accommodate it within the existing walls. Sometimes we have to expand. And there's a lot of other things that come into play as far as the the condition of the existing facility, if there are modifications that need to be made to bring it up to food safety standards, et cetera. Through that, we determine not only the equipment cost, the equipment installation costs, any building modification or expansion cost. We determine that overall cost, and then we develop a schedule around that. And then we can present this to a client with an understanding of where they are today in the production parameters, where they want to be, what needs to happen, how much is it going to cost, and how long is it going to take to do it. So they can do financial evaluations, determine their ROI, ROIC, or whatever parameter they're considering. A high-level review of the theory of constraints process. Appreciate your time, and please let me know if you have any questions. You can email me at sean.barr@theaustin.com. That's SEAN.BARR@theaustin.com. I look forward to hearing from you. Thank you.